Hello, my name is Panos. I'm part of the digital timber group of Grammasia College Research, and I'll be presenting the latest developments of COMPAS timber. For those who have heard it before, please bear with me. I will give a quick introduction of what COMPAS timber is. Then I will talk a bit about what's new in COMPAS timber, and then I will take the opportunity to present two projects that have been done using COMPAS timber. There is a third one waiting right outside that I know that later Gonzalo will present, so I'm not going to talk about that, but yeah. In a nutshell, COMPAS timber is a COMPAS extension, obviously, whose goal is to improve collaboration in timber construction. Our industry outreach has shown that significant inefficiencies lie in the data transfer between the various actors, where a linear data flow and an incompatible software mean information is lost in communication. A more ideal information workflow data flow would look like this, where communication is transparent, multidirectional, and lossless. We propose COMPAS Timber as a tool to help realize this improved data flow, and our ongoing development focuses on extending it as an open exchange format between commonly used software in the industry. What this means is following a common semantic model. A semantic model that describes the components through their properties. For example, a beam in COMPAS Timber is described through a frame and its length, width, and height. Whereas a joint it is described by the elements it connects, the type of the joint, and its attributes. More specifically, these joints are realized through the specific features that must be applied to each beam to enable the connection, or each element. And those geometric and CAM features that in COMPAS Timber would be referred to as processings are based on BTLX standards, ensuring seamless integration between design and fabrication. Now, what is BTLX? BTLX is a machine-agnostic modern standard used in timber construction industry, define machining instructions for timber elements, especially in automated and CNC fabrication, and is currently being developed by CIMA, CADWork, and LinkGlowCAM. This is what a BTLX processing looks like. A set of parameters define a machining operation, which a CAM software can interpret and assign an appropriate machining strategy to execute it. Having a look at an example, 3 different joints can be generated using the same BTLX processing in COMPAS Timber. And what is more important here is that this enables us to move from geometry in global space in the local space of the element. This is our current library of supported BTLX processings. And out of those, the ones highlighted have been implemented in the past year. So there's been a lot of development. And this is the point where I should mention that if somebody actually wants to contribute to COMPAS Timber, by implementing more BTLX processings, this is something that we could ask for, or defining new joints that can be generated using the already existing BTLX processings. Anyway, you can find a BTLX contribution guide in our GitHub page. Going back, using this extended list of BTLX processings, we were able to enrich our joinery library. And this is the various joints that we can actually handle in COMPAS Timber in T typology, L typology, and just one for X typology. Apart from these new developments, now in COMPAS Timber, actually, we can handle different types of elements. Whereas, if I'm not mistaken, the last time we presented here, we could only handle beams, whereas now we can also handle plate elements that can be described by 2 outlines. And even more, we can now handle group elements, or we can generate group elements such as slabs or wall elements, where a specific configuration set can populate elements in those walls or slabs, elements, and set with following a set of parameters such as stud spacing, stud dimension, sheeting inside, outside, etc. And basically, this means that now we can also handle group element interactions. And this is what Ken has been tirelessly working lately to basically enable this type of interactions where a wall and a wall would create a join, but then the features would be applied to the specific elements. Anyway, I realized that last year when we actually presented, we were just fabricating cache labs, or probably we just started fabricating cache labs. And I think this is a cool opportunity to present the final thing that somebody can actually visit in Dicentis. It's located in Dicentis in Graubünden, and it was actually prefabricated in RFL using this machine that is actually right next to me. Yeah, this is what a cache ladder module looks like. And basically you can see one right outside. The workflow using Compass Timber looks something like this, where a line model was generated by the students, including myself as well. I have to mention that this was a project done by the last year's MES students, including myself, with various collaborators. Yeah, a line model was generated. Then we were using Compass Timber actually to generate the beams and the joins, and therefore the BTLX processings that then we used in order to machine here. For the assembly, we actually used the COMPAS XR and the real-time visualization feedback developed by Alex, one of the researchers in our chair as well. Those are a bit more or less the numbers, if I'm not mistaken. So around 2,000 beams were milled, 72 assembly modules, 6 air modules that were put together here and then were transported in Dicentis and then flew on site with a helicopter. It took us around 1 month to mill everything, a bit more to assemble. But yeah. Yeah. There's some, maybe not. Maybe this is the other way around. And as you can see, basically their modules were actually flow on side. And this is a nice big from some assembly setting. And last before least, I would actually like to present the one before last projects that were done using COMPAS Timber, and this was done with the students of this year's MA students. And it's called Cadavre Exquise, which in English means the exquisite corpse. And basically draws its inspiration from a surrealist game that the surrealist artists used to play, where it's a collaborative activity where a piece of paper was folded into several sections, with each section assigned to a different artist. The game would begin with the first artist drawing something on their section, then folding the paper to conceal most of the contribution, leaving only a small portion visible. The paper was then passed to the next artist who contributed the drawing based on the visible fragment, and this process was continued until an unexpected and often surreal composition was revealed. And in a similar spirit, we applied the principles of the same game to an architectural project, where instead of folding a piece of paper, the folding was translated into a special division of the site, with each group assigned a specific area to develop their project. Like the surrealist game, each group could only see a minimal portion of the neighbor's designs, just enough to allow continuity and connection. And this could actually translate to data that was actually passed through the groups, which this encouraged collaboration through limited shared information, requiring students to coordinate and respond creatively to the boundaries of their spaces.
Kan je op de tafel even een briefje leggen met, weet je wel, instructies, weet je, wat jij verwacht? Volgens mij verwacht je, weet je, dat deze...
It apparently has not.
Kijk, ze staan nu post-rotate, dat ze zeg maar B-rotate weer staan.
But what was interesting in this project is that basically we used the majority of the joints that COMPAS Timber would actually support in its current state. Yeah.
Yeah.
That's it from me. Thanks a lot.
Yeah.